So, but to compute the eigenvector, so it is computationally not efficient, right? So, in practice, we use the iterative method. So we said that we're interested in this stationary distribution, right? We're interested in the stationary state of the matrix R. But to get this stationary means we multiply the matrix M, we're still getting similar R. So we just consider T plus 1 minus T. When the difference is smaller than some predetermined constant, we might say, oh, the R is converged. So R is following the stationary distribution, right? So we just give the epsilon, we get the difference. So using the L1 or L2, right? We repeat this, and we just return this without computing the exact eigenvector. We just keep iterating till the convergence. So in practice, we get the converged the vector R, like the less than the 100 computation iteration. So it is much more efficient compared to the eigenvector computation. So we start with this, keep compute, and we get some final score. So now it is time to think about the PageRank score always works. In other words, we have many different weird or exceptional graphs. So we need to see, are there any exceptional graphs that PageRank doesn't work? Here are two representative examples. The PageRank doesn't work. The previous one, so the simple one. So we have just what we have right now. So for example, dead ends. The pages that have no out links, for example, something like this, right? We propagate the PageRank score something like this, and then propagate this, but it has no outgoing links, right? So its PageRank score will keep increased, right? Because the score is not going out because it doesn't have out links. So it is called dead end. And another exception case is all links are within the group. So they're iterating, and maybe they have the groups have the more scores than the other, and it makes the distribution really weird. So to address the exceptional cases, for example, the dead ends, so make the matrix M as stochastic matrix. So in the previous example, we had something like this, right? This is the dead end. So when we construct the matrix M, assume that this is the third one, So they just have 0 values, right? Because it doesn't have the outlink. So it contradicts the stochastic, the matrix definition, right? The sum of the columns should be 1. So to avoid this, we just put some so artificial value to avoid this. So even though this is not the real, the outlink information, we just put this to make this assumption varied. At the same time, we don't have dead ends. Which is the same as like the randomly wired toward all the nodes available in the web. It's all the nodes. So with this way, this helps to escape from the dead end. The second exception case is spider trap. So all links are within the group, and to avoid this, so we put some probability beta, and we divide the probability like a beta and 1 minus beta, and with the probability beta we follow a link at random. Randomly propagate the paging score toward the anywhere. So with this way we can escape from the spider traps. And we also, with the probability 1 minus beta, we jump to the some random page. I'm sorry. Yeah, I explained in the approach way. So the randomly follow the link. So with the beta, we follow the existing link, the varied link with the beta. But still, it corresponds to the probability, the matrix M. So with the beta, we using the matrix M, the propagate the page rank score. The probability 1 minus beta, and we jump to the random page, any page. So this is the way to escape the spider trap. So let me give you the mathematical formulation about this. So with the beta, we following the existing link, so which is the same as the previous formulation, right? But with the probability 1 minus beta, and we can go to anywhere. This is the same as the number of the node, right? So you might wonder the choice of beta in practice 0.85, but still depends your input graph data. For the beta, we also call this is the damping factor. All right, so this is the example for this input. So consider this is from our the previous computation of the page rank. We assume that the beta is 0.8. We have this from this. We have this from this. So this means we can jump to anywhere from the node. With this probability, we randomly teleport toward anywhere. So this is jump. This is a teleport, right? And we can get this final probability. So this is the original page rank, the idea. So Larry Page and the Sergey Brin to propose this idea. So this is there's the initial paper. So that's it. So That is the page rank. So we have many variants, but let me just introduce the most popular ones. First one is the personalized page rank. So it sounds like something is personalized, right? So how do we compute that? We just, so compared to the original page rank, so we choose the so we use the 1 over n for the suffers, the rending part. So which means this one, right? We can randomly jump to, we can teleport to the anywhere, right? Teleport toward anywhere. That is cool. That is presented like this. But personalized means randomly we can go to some personalized the rending part. Not just, so it is all actually, so assume that we have the 10 different nodes available. So we just, it's something like this, right? They all have the same value. Personalized mean they randomly jumped to some specific part. It corresponds to some maybe it follows the preference of the system or some topic specific when you assume that the node represents the word, right? So, which is called personalized. It makes sense, right? And actually in Twitter, so in the Twitter, they recommend some people to follow, right? To quickly get the information, they use the personalized page rank. Right? It is fast to compute and quite accurate. So I'm not sure they still use the information, but they are using the personalized page rank. And when you recommend some new font and in your own application, so you have to compare the personalized page rank. So surprisingly, it is still very good in many cases. And we have another variant which is called random walk with restart. We can teleport to a specific node. So it is from restart, right? It is totally from the one node perspective, even though graph is constructed like this, right? We have this graph. So the page rank could be from the perspective of the one node, right? We start with the 1 0 0 0 0 and propagate the score considering the outbound link and randomly coming back to the node, right? Except this, everything else have just 0 values. We have use cases. So what is a use case? We can get the relevant score between two nodes. It is to compare how much the two nodes are similar, right? It is the use case for the random with restart. So maybe when you construct the word graph, right? The sports in Sonheung-min and Tottenham, you can construct this some words across graph. You may get some relevant score using the random walk with restart, and that is the application. And this has been used for many natural language processing papers as well. Maybe not anymore, so by having the deep learning. So all right. So that is the end of today's class. If you have any questions, please please let me know. Thank you for your attention. Have a great weekend. Bye bye.